We're continuing on here, chapter 10. We'll wrap it up hopefully today. Last time we talked about energy, and really a couple of aspects of it. We talked about enthalpy. And enthalpy is delta H, which is the change in enthalpy. And remember that when we do either calculate the delta H, or the delta H is given to us in an actual chemical equation, which is very common. Just by the sign of it will allow us to know whether or not a reaction is exothermic or endothermic. And again, if we get a delta H value that is negative, that means it's exothermic, and overall we do have heat and energy being released. If we calculate our delta H and it is a positive value, it will be an endothermic reaction, which means heat and energy will be absorbed. Now, there's several different ways you can kind of calculate delta H, and we're going to talk about another way here today as well. But last time we talked about a very common way, which is basically taking the difference between the enthalpy of all the products and subtracting from the enthalpy of all the reactants. So if you want to calculate the delta H of a reaction, you could take the delta H of the products minus the delta H of the reactants. And these are typically table values that you could look up, and they're oftentimes referred to as delta H of formation. And again, as we talked about, these are values a lot of times found in a table like in the back of your book, or usually most chemistry books. And when you do go to that table, much like most tables that you go to, and we even talked about it with specific heat as well, you want to make sure that you look up the substance that you're looking for, but you also make sure that you find it in the correct state. So if it's a gas, you want to get the gas value. If it's aqueous, you want to get the aqueous value, solid value, whatever it may be. The other thing that we saw when we did some of those examples was that most things that are really elements kind of in their natural form, not combined with anything else, things like H2O2, a piece of sodium metal, they typically will have delta H values of 0. So there's a lot of guys that will just be zeros for those values, and those are commonly things that are in their elemental form. The other also important thing that we talked about when you do this type of calculation is we do need to take the coefficients into account in a chemical equation. So for example, if we were to do it for this particular equation, when we look up the value for A, we would need to multiply it by 2. When we look up the value for B in the table, we would also need to multiply it by 3. So we do need to take the coefficients, which are the moles of each of those things, into account when we do this type of calculation. And that's a really important thing. So the idea here is what we talked about, which is a state function, which is, again, the only really important things, kind of where you begin and where you end. And again, in a reaction, products is pretty much where you end, and reactants is pretty much where you begin. So that's final minus initial sort of states. The other sort of aspect of energy that we talked about was the idea of specific heat. And specific heat capacity is the energy required to change 1 gram of a substance by 1 degree Celsius. There is an equation that goes with specific heat, which is Q is equal to ms delta T. Q being heat or energy in units of joules or calories. M is the mass, which is in units typically of grams. S is the specific heat capacity, which has units of joules per gram per degree Celsius, or calories per gram per degree Celsius. And lastly, the most important thing that we talked about really out of this equation is the change in temperature. And remember, when you do the change in temperature, you really just don't want to take the difference. Although numerically it will give you the same number, it is really important to do the final minus the initial temperature. And unlike most chemistry things, this will be usually in degrees Celsius. And it's really that aspect of it, as we talked about last time, which will determine whether or not really you will get a sort of a negative value or a positive value for Q. And if you do get a negative value or positive value, it also tells you whether or not the process is exothermic or endothermic. So if you get a negative value for Q, it's going to be exothermic. If you get a positive value for Q, it will be endothermic. Yeah. Yeah, so again, that is definitely one that comes up a lot and one that you should know, and that it was for liquid water. And the specific heat capacity for liquid water is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. That also, by the way, is, as we saw, the conversion factor to go from calories to joules. So if you remember the specific heat capacity for liquid water, you also have remembered the conversion factor to go from calories and joules. Is basically 1 calorie is 4.184 joules. Also remember, when we do look at specific heat capacity, as I mentioned earlier, you do want to get the correct phase. So for example, if we took water in its solid form, which is ice, the specific heat capacity is like 2 versus 4. So it does change depending on the state of it. And it's also a common sort of area. Later on in the semester, we'll do some specific heat sort of questions where, we may be in ice. So it's very common mistake. Sometimes people will use just the specific heat of liquid water. So it does change depending on the state. So make sure you are using the correct value. As we also saw last time, right, the larger specific heat capacity, the more energy it requires to change the temperature of that substance, right, by 1 degree Celsius. Any question on any of that stuff that we did last time? Okay, so then let us continue on. I think we're at another example. So why don't you take a couple moments here and do this one here. We have 294 joules of heat is transferred to a 10-gram sample of silver at 25 degrees. We're looking for what the final temperature of the silver will be. The specific heat capacity of silver is 0.24 joules per gram per degree Celsius. So take a couple minutes here, work it out, looking for a final temperature. Okay, let's take a look, see how you're doing. So obviously we're dealing with specific heat. So we'll start with our equation here. Q is equal to ms delta T. We have 294 joules given to us, which is Q. We have the mass given to us, which is 10 grams. This is our initial temperature of the metal, 25. We are looking for our final temperature in this case. And we do have the specific heat capacity given to us at 0.24 joules per gram per degree Celsius. So we really have this, and this, so we can really solve for the change in temperature. We could divide everybody over, basically. So that would give us Q is equal to, or divided by ms, equals our change in temperature, which means we have 294 joules divided by our mass of 10 grams, 0.24 joules per gram per degree Celsius being our specific heat capacity. Joules will cancel, grams will cancel. When we divide it, the degree Celsius comes to the top, and that is our units. So 294 divided by 10, and then divided by 0.24, going to give us like a 122.5 degrees Celsius. Now, technically speaking, I'm going to continue on with this calculation with this number, but I do want to think about sig figs. Sig figs wise, it should end up at how much? This number on top has how many sig figs? 3. This one has 3, and this one has 2. So technically speaking, if we were done with the calculation, we really should lay it up right about there, yeah, to that number, which would be about 120 if you really did round. I personally am not going to round at this point. I'm going to kind of remember that and kind of fix it up there at the end. What that really means, right, is that 122.5 degrees Celsius equals our change in temperature, and our change in temperature is final minus initial. So in this case, our final temperature minus 25 degrees Celsius, which was our initial. That means in this case, we're actually going to be adding it to the other side, not subtracting, right? So we're going to add it to the other side, and that will get us plus a 25. So I'll get us like a, I'll go to the top here, our final temperature of 147.5 degrees Celsius. First off, any questions on the calculation part before we clean it up? Okay, so at this point, we do want to kind of clean it up. So we do know, technically speaking, this number here really should have been something like 120, which has no decimal places, right? And this guy has no decimal places. So the last thing we did was actually add, which means we probably should take this to like $1.48. Yeah. And that would give us no decimal places in this particular case. Any questions on that? Now, clearly, if you round it to 120, you would end up with 145 at the end. I would take it. It's okay. But in this case, I just wanted to continue on with the number I had. Any questions on any of that? Yeah. What's that?
Like final lower than the initial, like cool down, and you get a negative value.
Yeah. So again, it's really class next chemistry class you take that you really do final minus initial. You absolutely can. Some people are taught to just take the absolute value, the difference of it. But for us, we do want to keep, when we do calculate something like heat Q, we do want to keep it either positive or negative, depending on if it's exothermic or endothermic. So if you always take the absolute value, there'll be no way that you get the negative on there unless you put it on at the end. So always do final minus initial. The reality is it is the same numerical value, but again, that is the place where the negative would come into play if it needed to be. Yeah. Other questions? This also does make sense, right? Our Q value here is positive, which means it is endothermic, which means we expect it to absorb energy. And because it's absorbing energy, we would expect the temperature to go up, right? So we started at 25, it went up to 148. If you did this and it went down, it shouldn't make sense to you because the energy value there again is positive. So it should be absorbing the energy. Any questions on that there? Okay. So let's talk a little bit about heat transfer. So when we do throw one object that's, say, hotter into another object that's cooler, there is going to be that heat that is transferred. And as we talked about, it's going to transfer from hot to cold. So the warm object there will cool down, the cold object will warm up, and they will meet there at the respective temperatures when it's all said and done. So this is a very common specific heat type of situation, and exactly like the experiment you're going to do today. And that is, let's say we took a beaker of water, and let's just say we had an initial temperature of 28 degrees. Let's say we had about 50 grams of the water. And let's say we took a piece of metal here that we heated up to like 95 degrees. And let's just say that initially it was like 35 grams of metal. So when I take this piece of metal and I toss it into the water here, because the metal is hotter than the water, the metal should lose energy, right? It should be given off energy. So it will be exothermic for the metal, which means all that energy will be deposited into the water as it goes in. And let's just say when we do that, the temperature of the water, we would expect to increase because it's gaining that energy. And let's just say it went to 30 degrees Celsius. Now, for the metal, once it goes for a swim, what will be the final temperature of the metal? The metal right now is sitting in the water that has come to rest at a temperature of 30 degrees in my example, which means the metal will actually also be 30 degrees, right? It'll be the exact same temperature. So in this situation, we could use the final temperature of the water that we put the metal into. That will also represent the final temperature of our metal, which would be 30 degrees in my example. So really there's two components here, and there's things that we definitely know about water that maybe we don't know about the metal. Let's say we wanted to know what the specific heat capacity of the metal is. which is exactly what you'll do later. So there's really two parts here. There is the metal and there is the water. And for the metal, we know the mass is 35 grams. We know the initial temperature is 95 degrees Celsius. We know the final temperature gets to 30 degrees Celsius. We do not know the specific heat capacity. That is what we're looking for. And really, we do not know Q at this point. For the water, though, we do know that the mass of it is 50 grams. We do know the initial temperature of the water was 28 degrees Celsius. We know the final temperature of the water went to 30 degrees Celsius. And we always know the specific heat capacity of water, which we just talked about a second ago, which is 4.184 joules per gram per degree Celsius. Again, that's the specific heat capacity for liquid water. So if we evaluate sort of what we have enough information to solve, we could see that for the water, we basically have enough information to figure out how much heat the water is going to absorb as a result of the metal going for a swim. So if we do that, Q for the water equals ms delta T. So in my example here, we got our 50 grams. We have our 4.184. And we have our final temperature, which is 30, minus our initial temperature, which is 28. And that will give us here with my made up numbers, let's see how we did, 4.184 times 30 minus 28. Gets us about, looks like 418.4 joules. Celsius will cancel, grams will cancel, leaves joules. Once again here, I'm not going to round, but if you were to sort of round, because I'm going to use this number here in a second, we should end up once again, this would have 3 significant figures, this would have 4. When we subtract this should be 2.0, which would be 2 significant figures. So we really should come here to about 420 in terms of the energy that was absorbed by the water. So that value represents the energy that was absorbed by the water. It is a positive value for Q, which makes sense. Again, it's absorbing that energy. So 100% of all that energy that the water absorbed came from the piece of metal, right? Which means how much energy did the metal lose? The metal would lose the exact same amount of energy. So we talked about sort of that perfect transfer of energy. If somebody loses a certain amount of energy, somebody else will gain the exact same amount of energy. The only difference is for the metal, it is losing it, right? Giving it off. It is actually exothermic. So there's a nice relationship when you do an experiment like this, like you'll do later, that Q of the metal, actually negative Q of the metal equals Q of the water, however you want to do it, don't really matter. Our Q of the water is equal to negative Q of the metal, which means we now know that the Q of the metal here is negative 418.4. I'm not going to round at this point. You could use the rounded number if you wanted to, but we now know it is negative. So now that we have that information from the actual water, we're able to use our specific heat equation one more time for the metal, and we can actually solve for what the specific heat capacity of the metal is. So Q of the metal will equal ms delta T, dividing both of these guys to the other side will give us the specific heat capacity of the metal will equal Q of the metal divided by m delta T. So putting in our numbers, Q of the metal minus 418.4 joules divided by our mass, which in this case for our metal was 35 grams. Now, this is really important. Again, as we were just talking about here, we do want to go final minus initial. So for the metal, the final temperature is 30 degrees. It cooled down. Minus the initial temperature, which is 95 degrees. That is important because when I do that, that gives me what type of number? This will give me a negative number, which works great with this negative. to turn my specific heat capacity back to a positive number. So again, important to make sure final minus initial puts the negative where it needs to be. If it does need to be there, we'll take 418.4, we'll divide it by 35, we'll divide it by 30 minus 95, and we will end up with a specific heat capacity of 0.18 joules per gram per degree Celsius, as none of those units cancel out. First off, question on the calculation. I ended up significant figures because my first calculation technically should have went here, which would have been a 420 that has 2 significant figures. This is 3 significant figures, and when we subtract this, we end up with like 65.0, which is 3 significant figures. Means we should end up with 2 significant figures, really based off of the first part of the calculation, although I didn't round until the very end, but I did keep track of it. Any questions on that there? Yeah. So we could use the specific heat of liquid water because that's like a value we know. And with knowing that value, what that allowed us to do was to basically figure out, in this case, how much heat the actual water absorbed a piece of metal in. And the importance of that is that then allows us to know by default how much heat was released by the metal. And by doing that, that then gave us the Q value that we needed, which was the only thing that was missing to allow us to solve for the specific heat capacity of the metal. So this is a very simple way that's done a lot. And like we'll do it today, and some coffee cups is all you need. And you basically just need a thermometer. And by just really following the change in the temperature of the water, you can figure out how much heat is released, say, by a piece of metal. You could even do it when you mix 2 sort of solutions together and it makes a reaction. Because most solutions are water-based, you could still use the specific heat capacity of liquid water, and just by measuring the difference in the temperature, doing a calculation like, Q equals ms delta T, you can figure out how much heat was released as a result of that chemical reaction, or absorbed as a result of that chemical reaction, if the temperature went the opposite way. So it's a really simple device where, because we know that specific heat capacity of liquid water, allows us to use that to sort of figure out backwards where the heat came from or where the heat was released and stuff like that. Exactly. So the idea of transfer of energy in these situations is we think of it as being perfect, like exact amount. If I threw in there number of energy, water. Alternatively, right, you could put something that's actually colder, right, into the water. So if you took the piece of metal out of a freezer and put it into water, at that point, the water is actually hotter than the metal, right? So it's actually the water is going to release the energy into the metal. Metal will warm up, right? Water will cool down. It would be opposite in that case, but as much energy as the water releases will be as much energy as the metal will pick up. Good. Yeah. Same question, or yeah, you get your question, I think. Yeah. Other questions on that? Okay, so this is a very common process, essentially exactly what you're going to do in lab. So exact calculation there that you're going to do in lab. All right. So I personally, now sometimes people will take this relationship here and essentially move like one of them to the other side, and that makes them all negative. I personally think it's much safer to kind of do it in 2 separate calculations, do everything for the water first, and then do everything for the metal second. What happens when somebody tries to kind of put them equal to each other, there's always a situation where the negatives and positives get mixed up by people and they really mess it up. So I would highly recommend kind of doing it like we just did in that example. So why don't you try it? So here's we're going to take a 110 gram sample of a metal at 55.5 degrees Celsius. We're going to put it into 150 milliliters of water at 23. It goes to 25.5. What is the specific heat capacity of the metal? The information you should know as well, density of water is 1 gram per milliliter. So that might be helpful here as well. All right, so take a few moments here. Basically, exact same thing we just talked about. See what you come up with. We got some water at a certain temperature. We're going to take something that is warmer. We're going to toss it in there. So again, it would be a good idea to kind of maybe break this up based on the metal and the water. So in terms of the metal, we do have the mass of it, which is 110 grams. It does have an initial temperature of 55.5 degrees Celsius. It raises 150 milliliters of water. I put the density there because if you take 150 milliliters of water and you times it by the density of 1 gram per milliliter, gives you 150 grams of water you started with. So we would have the mass of the water would be 150 grams. We do have the initial temperature here of the water, which is 23. It does go to a final temperature of 25.5 degrees Celsius. We also know the specific capacity of water will be our 4.184 joules per gram per degree Celsius. So again, that is something obviously you should know. Just like we were talking about, once I throw that metal into the water, the final temperature of the water will end up being what temperature here? The final temperature of that metal will be the same as the water that the final temperature of the water. So the final temperature of the metal again will be the same as it is sitting there and will cool down to the same temperature. Yeah. No, so it's usually a positive number. Yeah. Other questions on that? Okay. So once again, in this case, we are looking for the specific heat capacity of our metal. And once again, by just using the water, we do have enough information to figure out in this case how much energy the water is going to absorb. So that will be our calculation to start with. Q of the water here will be 150 grams times our specific heat capacity of liquid water. Once again, our final temperature being 25.5 minus our initial, which would be 23. And we will end up with here 150 times 4.184 times our 25.5 minus our 23. Gives us in this case 1,569 joules of energy. Again, here, I'm not going to round personally because I know I'm going to this number and continue on the calculation, but we do want to keep track, right? So once again, that is 4 sig figs. That is 4 sig figs. When we subtract this, that is 2.5, which is 2 sig figs. That means technically speaking, we should be somewhere at like 1,600 joules if we were to end the problem at this point and sort of round. Any questions on that? Now that is how much energy that the water absorbed, and it makes sense because it's positive. That means that the amount of energy that was released by the metal should be what number? Should be the exact same number, except that it should be negative 1569, as it is exothermic. Again, Q of the water minus Q of the metal. So exact same number, just change the sign, and that makes sense for the metal because it's releasing the energy, so it is exothermic. Now we got everything we need for the metal. So our Q of the metal, MS delta T, solving for S. S of the metal, once again, would be Q of our metal divided by M delta T minus 1569 divided by the mass of the metal, which is 110 grams. And once again, here we want to go final minus initial for the metal. So the metal ended up at 25.5 minus 55.5 degrees Celsius. Once again, that's going to give us the negative that we need to make it positive. So we will end up here with 0.48 joules per gram per degree Celsius, as none of the units there cancel. Once again, sig fig wise, we know from above, we should end here, which is 2 significant figures. This is 4 significant figures. And when we subtract this, we get something like 30.0, which is 3 significant figures. That means that our answer should end up with 2 significant figures when it's all said and done. And it is positive as the question. Specific heat capacity should always be a positive number. Question on that there. Again, pretty much the identical calculation for lab today. Yes, it's pretty much this one. Any questions on that? Questions on specific heat capacity or any of those things? Okay. So again, it's a very good process. The process uses a lot. And it really, as we will see here in a second, you really just need water and a thermometer and, you know, a pretty good couple coffee cups will work. And you could do a lot of energy sort of calculations. All right. So the next thing we're going to talk about then is a little bit about energy and nutrition. I think we touched upon it earlier, but remember that a capital calorie is a nutritional calorie, and that does equal 1,000 of the little calories, and that is 1 kilocalorie. So although we don't do too much with nutritional calories in here, if you do see that capital C, again, it is different than lowercase c, and it's basically 1,000 of them. A calorimeter is an apparatus that's used to determine the number of calories in food. So one way you could actually figure out nutritional calories there are, and basically do the difference in the water, basically take a thermometer and the difference in the water. So again, how much energy the water absorbs as it's burning. We know the specific heat capacity of liquid water. You could do a calculation. That'll tell you how much calories was released by that piece of food. You can figure out how many nutritional calories that would be per gram or whatever it may be. So an apparatus such like that is this is the bomb calorimeter because it's in a chamber with oxygen, so it sparks. We'll call it a chocolate chip cookie. We spark it, basically catches on fire. As it does, it obviously is going to release the heat to the surrounding water, which is in an insulated container, and we have a thermometer in there. And again, by just simply using that equation, Q is equal to MS delta T, and the specific heat capacity of liquid water, like I said, you're able to very simply figure out how much calories are being given off by the piece of food. Years ago in labs, they used to do an experiment similar to that. You take like a soda can, cut it off, put some water in it, take like a Cheeto or something like that, and put it underneath and set it on fire. And as the Cheeto burns, it obviously heats the water up in the soda can. And again, you can figure out how many calories came off of that particular potato chip or whatever it may be burning. Speaking of that, that's one way. Another very more common way that kind of calories are sometimes calculated is based on how much carbohydrates there are, protein, and fats there are in food. So these each have what are known as a caloric value. So carbs and protein, they both are 4 kilocalories per gram. And fat is a 9 kilocalories per gram. And remember that a kilocalorie is the same as a nutritional calorie. So it's basically how many calories per gram it is. So if you look at any of those nutritional labels on food, they usually will give you the breakdown of how many carbs there are, how many grams of it, how many grams of protein, how many grams of fat. And if you do that calculation, it will come up to the value that you see for how many nutritional calories there are per serving. In my experience on most labels, they round down the calories. But if you actually do it, it will give you that value that you see there. And again, here are the, once again, the nutritional calorie or the caloric value for each of those. Now, another very common way that we do these sort of energy experiments is like what you're going to do in lab today, which is actually just use a coffee cup, basically. A simple couple of coffee cups with a lid and a hole in it for the thermometer. It's a really good way to measure out how much heat and energy, again, is either being released or absorbed by a reaction. Like you're doing today, you could do something with metal and water. And like I mentioned before, you could actually, again, just take 2 solutions together, let the chemical reaction take place. You could do like a solution and put a metal in it or something like that. Again, because most solutions are water-based, they're aqueous in nature, which is water-based. We could use the specific heat for water in those reactions, and it will come out pretty good. Another nice thing about it is when we do these things at constant pressure, which is typically what happens in the lab, the pressure really doesn't change all that much. When you calculate Q in the lab doing this sort of procedure, you're also calculating the delta H of the reaction. So the enthalpy change will actually be the same. So you can actually figure out the actual delta H value by doing a very simple experiment like this with a couple of coffee cups. So back to nutritional calories for a second, just to show you a sample of the calculation here. If we had some oat bran cereal and we had 2 servings of it, and it contained basically 22 grams of carbs, 7 grams of fat, and 10 grams of protein for each serving, we would multiply the grams of the carbohydrates by the caloric value for carbs, and that basically gives us 88 calories. We'd do the same thing here for the fat by the caloric value, gives us basically 63 nutritional calories. And the same thing here for our proteins by the caloric value gives us 40 nutritional calories. Basically, to figure it all out, we add it together, and that gives us basically 191 calories per serving. And obviously, in this case, if we ate 2 servings, we would multiply it by 2. So we ate about 382 nutritional calories here in this serving of breakfast. And again, that is how they do calculate those values that you see on the nutritional labels by using those caloric values. Any questions on that there? All right, so another thing that's really important here that we're going to talk about is another way that we can calculate delta H for a reaction. So what we're going to talk about here at the end is what's referred to as Hess's Law. And Hess's Law is the idea that you basically build a reaction that you're interested in by using information from several individual reactions. So not all reactions take place in sort of one step, and maybe multiple steps that occur to get to the final reaction. And that will require us sometimes to have to manipulate some reactions. So you may have to reverse a reaction, may have to multiply a reaction by a number or divide by a number. So for example, here, this is ice going to liquid water. It takes 6.01 kilojoules per mole, basically. When we go from ice to liquid water, that is exothermic or endothermic. If you have an ice cube and it starts to melt, you need to put energy into it, right? So it's endothermic. It's picking up energy from the outside, right, to the ice cube, and it starts to melt. So that is why our value there is positive. If we feel bad about that, put it back in the freezer, and we want to go from liquid to solid in this case. That process is endothermic. We need to release energy to do so. When you release energy, the liquid water doesn't move as much, and they kind of clump together, and they go into the solid phase. So what happens when we reverse a reaction? These 2 reactions are reverse of each. The thing that happens with the delta H value is the sign changes. So if it was positive, it would go to negative. If it was a negative delta H, it would go to a positive value. So if it comes across a situation where you need to reverse a reaction, you basically need products on the reactant side or reactant on the product side. How the delta H value changes is the sign changes. Number stays the same, but the sign would change. So again, positive and negative if you flip it, or if it started at negative, it would go to positive if you flipped it. Now, in some cases, you may need to multiply an equation. Let's say we didn't need just 1 water in the ice phase. We needed 2. So as we go from here down to here, we're basically multiplying the entire reaction by 2. And how that affects the delta H value is you also multiply the delta H value by that number. So if you need to multiply an equation by a particular number, you then would multiply the delta H value for that equation by that number. And obviously, if we were needed to divide everybody here by a common number, the delta H, and that would give us water in the solid to water in the liquid. And when we divide that, delta H would be 6.0 kilojoules. So those are three things that you commonly have to do to equations when we're trying to calculate delta H using Hess's law. You have to reverse a reaction. Again, you change the sign on the delta H, the value stays the same. You may have to multiply by a common number. So you then would multiply the delta H by that number, or you may have to divide by a common number. You would divide the delta H by that number. Any questions on how to manipulate the equation? So really what this is for is, as I mentioned, what is referred to as Hess's law. And again, the idea behind Hess's law is this. You know, if you're looking at an overall reaction of A plus B goes to E plus F, it may not just happen in one step. So what might happen is a series of reactions. Maybe A plus B first makes C plus D, and there's a delta H value associated with that. Then maybe C plus D come together and make E plus F, and there's another delta H value associated with that step. When we would add these reactions together, or whenever you add these individual reactions together, anything that is on opposite sides of the arrow that's the same will either completely cancel out or reduce down. It's kind of like subtracting. You can think of the arrow as like an equal sign. So you would subtract it to the other side. So in this example here, C's on the left. It will cancel out with the C that's on the right. Here, the D's on the left, and it will cancel out with the D that's on the right. Once you cancel out, and it may not completely cancel, it may just reduce down. So if you had like a 4 on one side and then 3 on the other, you would end up with 1 on one side just by subtracting them. Everybody that's on the left-hand side of the arrow stays there. Everybody on the right-hand side of the arrow stays there. So in this case, we would have A plus B goes to E plus F. So whenever we add equations together, we cancel out or reduce down opposite sides, things on opposite sides of the arrow. Now, if we wanted the delta H for this reaction, it would actually be found by just simply taking the first delta H value plus the second delta H value. So if we wanted that delta H, you basically just add the individual delta H values together. Now, what's important is you may need to reverse a reaction like we just talked about, which means you need to change the delta H sign. You may need to multiply or divide by a number, which means you may need to adjust the delta H's values before you add them together. Any questions on that? So really what Hess's law is, it's like a puzzle, if you will. You have a bunch of individual reactions. You need to rearrange them in such a way that when you add them together, you basically get the reaction you're looking for. So once again, if we look here on the bottom, if we were to add these together, the water that's a gas would cancel, and then our H2 would stay on the left, our half of O2 would stay on the left, and our H2O that's liquid would stay on the right. We then didn't really do anything to these reactions, so we would just add our delta H values together, and that would give us, for this particular reaction, formation of liquid water, we get a delta H of minus 285.8 kilojoules. That means that process is endothermic or exothermic. It is exothermic. It's a negative number, so that it is exothermic. Any questions on that there? All right. So why don't you try one here? So what you want to do is, actually, we'll take this one together. So we want to actually make this reaction up on top. So this is basically what we want to make. And we want to figure out what the delta H value is for this. And we want to do it using these two equations. So really the best approach when you're doing a problem like this is to keep it really simple. Don't overcomplicate it. I'm going to go to the equation I'm looking to make. And I see I need carbon on the left-hand side of the arrow. I'm going to go down to the individual equations, and I see I have carbon over here. It's actually on the left-hand side of the arrow, and it's actually how much I need. There, I need 1 carbon when I'm done. I got 1 carbon there. That means I'm not going to do anything to this particular equation, actually. So I'm just going to simply leave that equation alone. I'm just going to rewrite it. And because I really didn't do anything to that equation, that means my delta H value is going to remain exactly the same. I didn't reverse it. I didn't multiply. I didn't divide. So I'm just going to leave it exactly the way it is. The next thing I'm going to look at is the CO2 here. And the CO2 I need on the right-hand side of the arrow. And the only one that has CO2 is the second equation. And it happens to be on the right-hand side of the arrow in this case. And I need one of them, and there's one of them there, which means in this case, I'm also not going to do anything to this equation. I'm just going to leave it exactly the way it is. And because I didn't do anything to this equation, the delta H value will once again stay the same, minus 283 kilojoules. At this point, I'm ready to add these together. So I'm going to look for anything that is on opposite sides of the arrow that's the same. So that is a CO and a CO. So those guys will completely cancel out. Once again, it's like subtracting CO to the other side. So it's like subtracting 2 to one side and you got 2, it equals 0. So here, everything else stays. So on the left-hand side, we have a carbon. We have a half and a half, which makes 1, O2. And we make CO2 in this case. Now, because I didn't do anything to these guys, I'm just going to simply add these two numbers together. And for this particular reaction, 110 plus 283 gives me a delta H value of minus 393 kilojoules. So in this one is pretty straightforward. You actually didn't have to do any manipulation to these equations, which does happen. Sometimes you may not have to touch them. Sometimes you may just need to move around one. Sometimes you may need to move around all of them. So don't be afraid to leave one alone, because you might just need to leave it alone, not actually do anything with it. But it can be a situation where you need to play with all of them. This reaction would again be exothermic, as we ended up with a negative 393 kilojoules value there for our delta H. Any questions on that one? Yeah. We added them. Yeah. So when you add them together, you basically can subtract off anything that's on opposite sides of the arrows, because you could think of the arrows like an equal. So if you think about it, kind of like you have a CO on one side and a CO on the other, and you think about this like an equal sign, you're basically going to subtract CO to both sides and they will cancel out. Is basically what you're doing. Kind of like if you had 4 on both sides, you would subtract 4 to the other side and it would cancel it out basically. Other questions? All right, so why don't you try one where you will need to do some manipulation here. So based on these two equations, we want to end up with the equation on the bottom. And once you manipulate it, we want to figure out what is the delta H value. So take a couple minutes and see what you come up with. So again, may require you to multiply, reverse, maybe not do anything. So we basically want to build the bottom equation from the top two equations. So see what you come up with. Okay, let's see how you're doing. So again, best approach when doing these type of things. Sometimes people freak out. There's a lot of individual equations. It's just to go to the equation you're trying to build and just make sure everybody's on the correct side and you have enough of everybody. So I'm going to start with the N2, which is on the left-hand side, and it is in this equation. But I need 2 of them, and I only have a half, I think, up there. So to turn that into a 2, I need to multiply this entire equation by 4 will get me 2, right? So 4 divided by 2 is 2. When I do that, I'm also going to have to multiply my delta H value by 4 as well. So we're going to multiply everybody by 4. That would give me 2 of the N2 plus 12 divided by 2 is 6H2. Goes to 4 of the NH3. And now my new delta H value is going to be minus 46 times 4. And that's going to give me minus 184 kilojoules. Any questions on that so far? Next thing I'm going to do is simply go to the next thing in my equation I'm looking for, which is I want 6 waters in the gas state. And it's on the left. So it's on the left here, but again, it is not 6. So I'm going to need to multiply the bottom equation by 3. And because I'm multiplying the bottom equation by 3, I will also need to multiply the delta H value by 3 as well. When I do that, that gives me 6 of the water No plus, just an arrow. That gives me 6 of the H2 plus 3 of the O2. My delta H value here will now be 3 times 484. So that's going to be 484 times 3 gives me 1452, it looks like, kilojoules. Any questions on that so far? Now, if I did this correctly, I'm clearly out of equations, right? So if I did this correctly, everything should cancel out and I should be left with this equation. So let's see. We do have 6 H2s on the left, which will completely cancel out the 6 H2s on the right. And I think that's all the canceling. So that leaves me, everybody on the left stays there. So 2 N2s plus 6 waters on the left-hand side of the arrow goes to 4 NH3s on the right plus 3 O2s. So 2 N2s, 6 waters, 4 NH3s, and 3 O2s. So I successfully built the correct equation. Any question on that? Now that I have adjusted my delta H values for everything I did to find the delta H of this reaction, I'm simply just going to add those values together. So that's going to give me minus 184 plus 1452 gives me 1268 kilojoules as a delta H for this reaction. Any questions on that? Yeah. So the goal here is to end up with this equation. And for example, in this original equation, there was only 1/2, right? That doesn't equal 2. So the only way to get a half to equal 2 is you have to multiply it by 4. So because I had to multiply that N2 by 4, I actually got to multiply everybody in the equation by 4. So that's where that came from. The one underneath was because in the end, I needed 6 waters. I only started with 2. So in order to get me the correct number of waters, I had to multiply the water by 3. But once again, we got to multiply everybody there in the equation by it as well as a delta H. Yep. Other questions? So again, people sometimes freak out on the Hess's Law thing. You just want to keep it simple. And again, just make sure everybody ends up on the correct side of the arrow and you have the correct amount. And the main thing is to keep track of what you did to get everybody there. So why don't we try another one here? Let's see. All right, so using the top 3 equations, we want to build this equation on the bottom, and we want to figure out what is the delta H value here. So once again, you may have to multiply, may have to divide, may have to reverse the reaction. So give it a go, see what you come up with. Simply, I need carbon on the left-hand side, and I just need one of them. And I see it here in this equation, and that's exactly how it is. So I'm not going to actually do anything to the top equation because it's exactly the way I need it. I'm just going to rewrite it. So carbon plus oxygen. I'm not going to write all the other stuff to make it not so busy. And because I didn't do anything to it, my delta H value will remain the same. I'm then going to go to my next guy. I need sulfur on the left, which it is. But here I do need 2 of them, but I only have 1. So that is going to require me to multiply that entire equation by 2. And because of that, I will also need to multiply the delta H value by 2 as well. That will give me 2 sulfurs plus 2 oxygens, gives me 2 SO2. Taking my delta H value, taking the minus 296.1 times in it by 2 will give me 592.2. That's negative 592.2 kilojoules. Any questions so far? So lastly here, I need the carbon, sulfur, CS2 on the right-hand side. Here it's on the left-hand side. So I do need to reverse this reaction, but it is the right amount that I need. I just need 1. So I'm going to reverse it. So our reactants become our products become our reactants. So we're just going to write it in the opposite direction like this. Now, because I reversed that reaction, what happens to the delta H here? It becomes positive, right? We just changed the sign. So the delta H value here will be positive 1072. Any questions on that there? Now, if I did this correctly, everything should cancel out, and I should end up with the equation I'm looking for. CO2 will cancel. We have SO2 will cancel. That is 1 O2 and 2 more make 3, which cancels out with this guy. And that leaves us a carbon on the left and a couple of sulfurs and CS2. Now all that's left to figure out the delta H is to add our delta H's that we adjusted based on what we did. That would give us minus 393.5 plus negative 592.2 plus a 1072. Going to give us 86.3, looks like, kilojoules here. If you want to be significant figure-wise, technically that's a whole number, so 86 kilojoules would be probably good. That means that this reaction is endothermic, right? Question on that there. So usually when you run out of equations and you've done either stuff to it or left alone and you add them together, everybody else should kind of fall into place based on multiplying or dividing, stuff like that. Question on Hess's law there. Okay, we have a couple of slides to go here. We're just going to talk about a couple of things on them to wrap this chapter up, and then we'll talk about a couple more things. Then I'll let you go here. Any questions though on this here? Okay. So just to kind of conclude this chapter here and stuff we've been talking about, delta E is the change in internal energy, and it is equal to Q, which is heat that you could calculate using the specific heat equation. And W here is work. And it really does work kind of the same way as everything else. If heat and work is added to a system, then it'll be positive. So kind of like it's endothermic, everything's being added. And if it is removed or released, it will be a negative value. So kind of like an exothermic type process where things are being released. Now, this little topic here, you'll talk more about in Chem 1B. It is entropy, which is different than enthalpy, and it's abbreviated as a delta S. And basically what entropy is the amount of disorder or randomness that occurs. The more disorder that happens, the more entropy that you have. Entropy is the amount of randomness, and the most often that we see it and most commonly see is like situations like this. When we change states, as we go from solid, things are really organized. As you go from solid to liquid, things get more disorganized, right? A lot more disorder, and the amount of entropy increases. As you go from liquid to gas, things start flying around, so a lot more craziness, a lot more disorder, and that also increases the entropy. And lastly, when we increase the temperature, everybody gains more energy. They start moving around a lot faster, also increases the entropy. We're not really going to go too much, or you have to worry too much about entropy.